Welcome back, everyone. Consider this explainer to be your intensive, deep dive masterclass on Phase 4 of our curriculum. We are getting right into the 5G new radio physical layer and numerology. Look, if you're driving any kind of enterprise digital transformation, understanding the actual physics and the core network mechanics we're about to cover is absolutely essential. We're going to take all this complex theory and connect it directly to how you architect truly resilient, carrier-grade networks.
Here is our roadmap for today. We'll start with objectives and context, roll right into flexible numerology, then frames and mini slots, migration paths, SON and scalability, and we'll wrap up with your lab prep and assessment.
All right, Section 1, Objectives and Context. Let's set some expectations.
By the end of our session today, you need to be able to confidently demonstrate 3 very specific outcomes. First up, you've got to be able to describe the core 5G network functions. Second, you need to clearly explain the complex trade-offs involved in flexible numerology. And finally, I need you to be able to trace a complete attached call flow, all the way from the user equipment right up to the core. Make sure you've got these down, because this is exactly what you'll be evaluated on. But before we get completely lost in the physics of it all, we really need to ground ourselves in the strategic context, that classic build versus buy dilemma. When you're designing these networks, you're facing a massive architectural choice. On one hand, you've got open and interoperable systems, like Open RAN. These rely on shared standards, which is great for fostering competition, driving down costs, and sparking innovation. But they can be pretty complex to manage, and they definitely introduce varying security surfaces. Now, on the other hand, you have sovereign digital ecosystems. These prioritize strategic autonomy. They give you highly consistent performance because they operate as a single, tightly integrated block. The trade-off, though, is that they might limit your long-term competitiveness, and they carry a risk of technological isolation. So keeping this strategic landscape in mind is crucial as we move forward.
Moving on to Section 2, Flexible Numerology and Subcarrier Spacing.
With our strategy set, let's look at the actual foundational tech powering these networks. Honestly, the biggest, most fundamental shift from 4G to 5G is the scalable architecture. Back in LTE, we were completely locked into this rigid 15 kHz subcarrier spacing. It was basically a compromise so we could handle voice and data at the same time. But 5G, it breaks those rules. It scales from 15 kHz all the way up to an incredible 240 kHz. This means the network can adapt instantly to vastly different frequencies. And to help user equipment manage this massive spectrum, 5G introduces something called bandwidth parts. This allows the device to only monitor the specific active bandwidth it needs, which is a total game changer for drastically reducing RF processing load and saving battery power.
3GPP actually maps out all this flexibility into a really clear blueprint using the Greek letter mu, which goes from 0 to 4. So mu equals 0, that's our legacy 15 kHz spacing. Mu equals 1 is 30, mu equals 2 is 60, and it doubles all the way up to mu equals 4, giving us that 240 kHz spacing. I really want you to pay attention to the cyclic prefix. Notice how it changes proportionally to maintain orthogonality and keep multipath interference in check. Seriously, make a mental note of this relationship, because it is absolutely going to pop up on your terminology quiz.
Now, there is a catch here. You can't just slap any numerology onto any physical channel. The rules are actually pretty strict. For example, if you take that massive 240 kHz spacing, mu equals 4, that actually isn't supported for carrying your standard user data on the PDSCH or PUSAGE. And it goes the other way too. If you look at mu equals 2, the 60 kHz spacing, you can't use that for synchronization signals like the PSS and SSS. You always have to map the specific numerology to the exact job that channel is designed to do.
Let's jump into Section 3, Frames, Slots, and Mini-Slots in the Time Domain. Let's see how the subcarrier spacing actually builds out our understanding of time. In 5G, every single radio frame is strictly 10 milliseconds long, and it's divided into 10 1-millisecond subframes. That part is a constant, it never changes, but the slot duration inside those subframes, that changes dynamically. As you increase the subcarrier spacing, you are physically compressing the slot duration. If you double your subcarrier spacing, you precisely halve your slot duration. This inverse relationship is the secret sauce behind 5G's ultra-low latency at high frequencies. And this microsecond flexibility is just incredibly powerful when you're using time division duplexing, or TDD, because it lets you dynamically assign uplink and downlink slots across really wide millimeter wave carriers.
So, let's actually put this into practice and do a quick interactive calculation together. Imagine we are deploying a network using mu equals 3, which is our 120 kHz spacing. What is our slot duration going to be? Well, our standard 10 millisecond frame is now dividing into 80 individual slots. So if you divide 10 milliseconds by 80, You get exactly 0.125 milliseconds per slot. Just think about that for a second. Compare that to the full 1 millisecond block we were stuck with in LTE. But you know what? For some cutting-edge use cases, even 0.125 milliseconds is still just too slow. And that is exactly where mini slots come in. A mini slot is this super short transmission made up of just 2 to 7 symbols. So instead of waiting around for the next full slot boundary to start sending data, the network can instantly punch a mini slot right through the active frame. This drastically slashes the transmission time interval. If you are rolling out an ultra-reliable low-latency communication system, let's say you're guiding high-speed robotic arms on a smart factory floor, these mini slots are quite literally what prevent a catastrophic collision.
All right, Section 4, Migration Paths from NSA to SA. To see how all these physical layer concepts actually plug into the core network, we really need to talk about migration paths. For the vast majority of early enterprise deployments, you're going to run into the non-standalone architecture, or NSA. In this setup, your legacy LTE eNode B acts as the master anchor. So the user equipment powers up, connects to the existing 4G core, does all its measurement reports, and then the eNode B signals it to add the 5G NR cell as a secondary node just to boost the data rate. It's a highly pragmatic bridge to get 5G speeds quickly, but at the end of the day, it still heavily relies on that old 4G core. But eventually, your goal is to migrate to a true standalone, or SA, access flow. This is where the magic really happens, because the device talks directly to the 5G G-Node B and the 5G core. It kicks off by decoding the synchronization signal block to lock in the timing, which is immediately followed by the random access procedure. Now here's a critical engineering detail. To make this step latency resistant, the terminal randomly chooses a preamble ID at each retransmission, which is brilliant because it effectively avoids collisions. Once everything is synchronized, we request the RRC connection. The network sets it up, and finally, the device fires off its registration request straight to the core.
As soon as that registration hits the core, we've got to lock the session down securely. The access stratum, or AS, security procedure happens right between the device and the G-Node B. Once the encryption and the integrity protection are fully confirmed, the G-Node B sends the RRC reconfiguration message. This specific message is the trigger that actually establishes the default PDU session, allocating the exact network resources the user needs to start pushing real data.
That brings us to Section 5, SON, Scalability and Automation. When you start thinking about managing these microsecond slot changes, coordinating massive MIMO beams, and handling incredibly complex call flows across thousands or millions of devices, well, human operators simply cannot keep pace with that. This is why self-organizing networks, or SON, are essentially the lifeblood of this ecosystem. You've got 3 deployment styles here. There's centralized SON, which runs up in your management layer. Then there's distributed SON, which sits right down inside the network nodes themselves. And finally, hybrid SON, which spans across both. By utilizing these tight, closed control loops that are constantly monitoring, analyzing, deciding, and executing, the network can literally heal itself, optimize its own beams, and tweak parameters with zero manual intervention.
And this level of automation is inextricably linked to the scalability of the 5G core. Because the core is fully cloud-native, these automated SON scripts can instantly spin up virtualized functions on demand. You have the Access and Mobility Management function, or AMF, handling the signaling. The Session Management function, the SMF, is taking care of session modifications. And the User Plane function, the UPF, is routing the actual data packets. By completely splitting the control plane from the user plane in this way, you allow the network to scale its resilience immensely, especially during sudden, massive traffic spikes.
And finally, Section 6, Lab Prep and Assessment. Let's talk about applying all this theory. For your hands-on instructional activities today, you are going to be spinning up minimum viable products using open source cores. You can use free 5GC or Open 5GS within your containers. Your specific deliverables for this phase are to use a PHY simulator or a software-defined radio testbed if you prefer to measure latency versus throughput. I want you to directly compare mu equals 0 against mu equals 3. And finally, you need to submit a fully documented lab report, which must include a Wireshark packet capture of that random access flow we discussed earlier. So as you head into the lab to start building out your proof of concept today, I want to leave you with one big question to chew on. You can absolutely build an MVP on an open source core, but what is your strategic, incremental migration path to a fully automated carrier-grade network, one that is actually capable of guaranteeing strict enterprise service level agreements? Really think about how the physical numerology, the split architecture, and the automation loops we covered today will scale up to meet your ultimate digital transformation goals. Good luck in the labs, engineers, and I will see you in the next phase.
Welcome back, everyone, to Phase 5 of our Advanced Masterclass curriculum. Today, we are bringing together absolutely everything we've learned so far in this explainer. We're going to trace some complex call flows, analyze the literal physics of numerology, and get your actionable lab assignment set up. So if you want to truly understand how a 5G network operates under the hood, you are absolutely in the right place. Let's get into it. Here's a quick look at our agenda for today. We'll be hitting the 5G strategic context, 5G core and NGAP, numerology and subcarrier spacing, cell search and RATCH, the standalone registration call flow, and we'll wrap up with handovers and lab execution. Basically, by the end of this, you'll be able to trace a complete attached call flow from scratch and confidently contrast an open source core with a fully carrier-grade system. All right, Section 1, the 5G strategic context. Because to start, we really have to ground these highly technical procedures in real-world business value and strategic execution. Network architects are constantly weighing these build versus buy trade-offs, right? On one side, you've got your minimum viable product, or MVP. This is where you might spin up open source tools. Think Free5DC or Open5GS paired with SRSRN, just running locally on containers. It's a great proof of concept. But on the flip side, you have full production. We're talking about Rakuten's massive cloud-native 5G rollout, or maybe a super high-density O-RAN deployment in a sports stadium. These are resilient, carrier-grade networks, usually managed by the likes of Ericsson or Nokia, and they are bound by very strict service-level agreements. Understanding both approaches is absolutely critical for your toolkit. And the core architecture brilliantly illustrates the strategic advantage of 5G. The entire core network is built on stateless network functions, meaning compute resources are completely decoupled from storage. The unified data management function safely holds all that subscriber data, which allows for literally unlimited linear scalability. Plus, you get the extreme resilience needed for demanding digital transformations, like running a fully automated smart factory, for instance. Moving right along to Section 2, 5G Core and NGAP. Now that we have a feel for the overall topology, let's zoom in a bit on the actual protocols making this core operate so seamlessly. Enter the NG Application Protocol, or NGAP. You can really think of NGAP as a bustling orchestra conductor. Its entire job, its sole purpose, is ensuring perfect harmony, efficient resource allocation, and completely secure messaging between those frontline radio troops, the GNB, and the brain of the network, specifically the AMF. What's super interesting about the NGAP architecture is how it's physically stacked over the N2 interface. If we look at the transport layer, NGAP utilizes the Stream Control Transmission Protocol, or SCTP, to guarantee highly reliable message delivery. And then, right below the application layer, it leverages TLS for just ironclad security. We're talking strict authentication and confidentiality. Because let's face it, without a secure, reliable channel, all of 5G's big promises would just fall apart completely. Now, those in-gap messages are constantly talking to some really essential network functions. The AMF acts as the control plane anchor. It handles all the authentication. Then you have the SMF, which manages the actual session establishment and the data tunnels. The UPF does the heavy lifting, routing and forwarding the actual user packets. And finally, the PCF handles your quality of service and policy data. The huge takeaway here is that these specialized functions split the control and user planes entirely. That split is the foundational secret to 5G's incredible reliability and scale. Okay, Section 3, Numerology and Subcarrier Spacing. Let's pivot to the physical layer physics for a second and see how this builds incredible flexibility right into the radio interface. We call this concept numerology. Back in the 4G LTE days, we were locked into a very rigid single subcarrier spacing of 15 kilohertz. It was a compromise, really. But 5G introduces scalable numerology. This allows the radio network to support vastly different services, everything from massive IoT deployments to ultra-high-speed broadband, and it can do it across very different carrier frequencies. It's a real game changer. But this flexibility doesn't mean it's just a free-for-all. Not every numerology can be used for every channel. For example, if you're using numerology 4 at a massive 240 kilohertz, well, it supports synchronization channels, but it explicitly prohibits data channels like the PDSCH. Conversely, a 60 kilohertz spacing fully supports data, but not sync. So when you're designing network slices, you have to keep these physical limitations top of mind. Furthermore, as you mathematically increase that subcarrier spacing, it naturally decreases the slot length. The slot literally shrinks as the kilohertz go up. And this allows us to utilize what we call mini slots, which can be just 2, 4, or 7 symbols long. By using a mini slot, we completely eliminate the need to wait for a standard slot boundary. That drastically cuts down transmission delay, which is absolutely vital for ultra-reliable low-latency communications, or URLLC. Up next, Section 4, Cell Search and Ratch. With all the physics established, it's time to actually execute. How does a user's phone find and talk to this incredibly complex network?
It all comes down to a crucial 4-step synchronization dance. A device can't just wake up and start transmitting. First, it has to tune to the carrier frequency and hunt for the synchronization signal block, or SSB. It decodes the primary and secondary sync signals just to get the cell ID and timing. Then, using that, it demodulates the master information block to figure out the subcarrier spacing. Finally, it uses all that data to hunt down SIB1, which reveals the network's actual identity, like the PLMN ID. Only after this entire sequence does the device even know what network it's looking at.
Once it actually knows the network, it has to establish uplink sync. It does this via the random access, or RATCH procedure. We're looking at the default contention-based mode here. First, the device shouts a random PRATCH preamble. That's message 1. The tower hears it and replies with a timing advance and a grant to speak, message 2. Then, the device formally requests an RRC connection, message 3. And finally, the tower resolves any collisions and assigns an identity, message 4. If a collision happened, only one UE succeeds and the others time out. For those of you doing the live labs, capturing this exact 4-message handshake in Wireshark is your primary objective. Which brings us to Section 5, Standalone Registration Call Flow. This is really the capstone of our masterclass today. Immediately after that reach procedure finishes up, context setup and security take over. Once the radio resource control, or RRC, is actually connected, the GNB tower acts as a secure conduit. It bridges the device directly to the 5G core, specifically engaging the AMF and the authentication server function to rigorously authenticate the device before a single drop of user data is allowed to pass. Let's break down the highlights of that attach sequence. First, the device sends a NAS registration request, including its concealed identity, straight to the AMF. Then we get mutual 5G AK authentication and a security mode command. Following that, the AMF officially accepts the registration with the new 5G GUTI. The GNB then performs an RSC reconfiguration to set up dedicated radio bearers and QoS. And finally, the user equipment requests a PDU session. The SMF and UPF allocate an IP address, and boom, we've traced the flow from a cold start all the way to a PDU session establishment where end-to-end user data can finally actually flow. Objective complete. And finally, Section 6, Handovers and Lab Execution. Let's quickly cover device mobility and then detail your actionable deliverables for this module. When we talk about mobility architectures, you have to distinguish between 2 main scenarios. An intra-NR handover happens when a user moves between 2 5G towers. Those towers communicate directly with each other over the XN interface to transfer the user context completely seamlessly. But what happens if you drop out of 5G coverage entirely? Well, that's an inter-RAT handover. That relies on the N26 interface, which acts as a bridge deep in the core between the 5G AMF and the legacy 4G EPC MME, seamlessly coordinating the context to keep your session alive. Which brings us right to your module assessment and lab deliverables. It is time to put all this theory into practice. Your assignment is to spin up an open-source free 5GC core and an SRS-RAN GNB right on a local containerized testbed. You're going to execute a live device attach, capture the packets using Wireshark, and physically annotate the signaling steps we just covered, from the RSC setup and registration request right through to the PDU session. On top of that, you'll need to pass the module quizzes covering critical terminology. I'm talking STAP, 5QI, and the N1, N2, and N3 interfaces. This is how we prove enterprise readiness. As you dive into your hands-on labs this week, I want you to really chew on this final question. When scaling your architecture from a simple, containerized lab MVP to a massive carrier-grade network with incredibly strict SLAs, how will your approach to slicing and numerology need to evolve? Keep that strategic context in the back of your mind as you capture those packets. Best of luck with the labs, have fun with it, and I will see you in the next explainer. Welcome to this explainer. Today, we're diving headfirst into the really advanced features of 5G, and we're even going to map out the strategic roadmap to 6G. If you're an enterprise learner looking to figure out exactly how to design, assess, and actually deliver these next-gen networks, well, you are definitely in the right place. We're going to take these incredibly complex capabilities and translate them into actionable strategies for your organization. Let's get into it. So here's our game plan for today. First, we'll tackle the physical layer and beamforming. Second, we'll look at network slicing architecture. Third, we'll break down self-organizing networks. And finally, we'll take a trip down the road to 6G. All right, let's jump right into Section 1, physical layer and beamforming. To kick things off, our main objective here is to understand how the physical layer really sets the mathematical foundation for all these advanced 5G capabilities. I mean, this is where the magic of manipulating the radio signal actually happens. And honestly, it's absolutely crucial knowledge if you're looking to calculate network performance or, say, design a proof of concept deployment. Now, unlike legacy LTE, which was pretty rigidly locked into a 15 kHz subcarrier spacing, 5G New Radio brings a highly flexible architecture to the cable. We're talking about subcarrier spacing that scales all the way from 15 kHz up to a massive 240 kHz. Now, for your problem-solving assessments, here is the golden rule you need to remember. As the subcarrier spacing scales up, the slot duration proportionally shrinks. It drops from 1 millisecond all the way down to a blistering 0.0625 milliseconds. This specific mathematical trade-off, that's exactly what enables the ultra-low latency communication you need for advanced enterprise apps. So there's this exact inverse relationship between wider subcarrier blocks and rapid slot durations. And it gets better. In 5G and R, you can actually utilize what are called mini slots. This means transmitting on just 2, 4, or 7 OFDM symbols instead of sitting around waiting for a whole full slot to finish. Think about it. When you're designing a smart factory MVP or any high-speed automated environment, these little microsecond savings in the physical layer are exactly what prevent those dreaded latency bottlenecks. Moving beyond just numerology, 5G relies heavily on beam management and massive MIMO. This is especially true when you're operating in those higher frequency millimeter wave bands where path loss can be pretty severe. Basically, 5G uses these massive antenna arrays to form really narrow, highly targeted beams. It's kind of like replacing a floodlight with a laser pointer. This drastically improves your signal-to-noise ratio. The network uses both analog and digital beamforming to juggle dozens of distinct data streams per cell, keeping users spatially separated. But to actually pull this off, the transmitter needs to constantly know what's going on with the channel. It requires ongoing channel state information, or CSI, feedback right from the device. If you're ever simulating a MIMO setup in a lab, maybe using MATLAB, tracking this exact beam alignment between the device and the antenna is going to be your primary focus. But, the real world is messy. What happens when a sudden urban blockage, like a massive passing truck or a closing warehouse door, suddenly interrupts that narrow beam? Well, that brings us to the 4-step beam recovery procedure. Step 1 is beam failure detection, which gets triggered the second the error probability on the control channel spikes too high. Step 2 is candidate beam identification, where the device rapidly scrambles to search for a new beam pair. Step 3 is firing off a recovery request transmission back to the network. And finally, Step 4 is the network's response. Because 5G handles this directly at the lower layers of the protocol stack, it can swiftly recover from sudden blockages way faster than those traditional, clunkier, higher-layer radio link failure protocols. It's a real game-changer for network resilience. Okay, moving right along to Section 2, network slicing architecture. So once we've got this flexible, beam-formed physical layer running, we can start carving it up to meet very specific business needs. And this brings us to a wonderfully heavy technical acronym that you are definitely going to see on your terminology quizzes, SNSSA. That stands for Single Network Slice Selection Assistance Information. When a user device connects to the network, it signals this specific info. Then, the Access and Mobility Management function, the AMF, teams up with the Network Selection function to use this data, ensuring the device gets dropped onto the exact optimal virtual network slice. And get this, a single device can actually be configured to connect to up to 8 distinct, completely isolated slices simultaneously. No way, right? But it's true. To put it into perspective, network slicing is basically like configuring multiple virtual computers on the exact same physical computer. These slices all run on a shared physical core and radio network, sure, but they act as entirely independent end-to-end networks. For communication service providers, this is the holy grail. It allows them to offer highly differentiated service level agreements, or SLAs. They can spin up one high-throughput broadband slice for consumers watching videos and simultaneously run an entirely isolated, ultra-reliable, low-latency slice for an enterprise's automated factory floor. Here's an actionable case study for you regarding how we route the user plane function, or UPF. For an everyday mobile broadband user, their traffic gets routed all the way to the UPF sitting back at the central core site. However, for a user that absolutely needs local, ultra-low latency service, let's say a robotic arm on an assembly line, the UPF is positioned right out at the network edge. This clever separation of the control plane and the user plane is exactly what allows 5G to scale so efficiently and securely for massive enterprise deployments.
So let's do a quick reality check here. With hundreds of flexible numerologies, thousands of dynamic tracking beams sweeping around, and customized virtual slices routing traffic to the edge, how can a network possibly manage itself? Well, the hard truth is, manual human tuning of these highly dynamic, beam-centric parameters is just completely impossible.
Which leads us perfectly into Section 3, self-organizing networks. The answer to all that immense, grain-melting complexity is a vital management layer known as SON, or self-organizing networks. SON is an automation framework that basically enables cellular networks to configure, optimize, and heal themselves with almost zero human intervention. It pulls this off by continuously closing control loops based on standardized management models. And it's really important to note here that 5G SON extends way beyond the old LTE cell-centric scope. It is specifically built from the ground up to handle the massive complexity of a beam-centric new radio environment using advanced automated algorithms. Let's quickly break down the core SON use cases you need to know. First, plug-and-play RAN self-configuration. This means new base stations can automatically integrate into the network with practically zero manual backhaul configuration. Next up, self-optimization, where operational nodes are constantly auto-adjusting their algorithms, antenna tilts, and power levels based on real-time KPIs. Then we've got self-hearing. If a node suddenly fails, the network automatically bridges the service gap by tweaking adjacent cell boundaries and rerouting traffic around the failure until you can get a permanent physical fix in place. And finally, capabilities like beam-aware automatic neighbor relation, which ensure perfectly seamless handovers without any human mapping required. When you sit down to evaluate those tricky build versus buy trade-offs for a new enterprise network, you'll find the operational and cost-saving benefits of SON are just massive. We're talking faster rollouts, way fewer dropped connections, lower network congestion, and absolutely vital operational energy savings. Now, the official standards tell the network what to measure, for sure, but the actual magic, the control logic, that entirely depends on the ingenuity of the SON algorithms deployed by your vendor, or whatever open source stack you choose to run. And finally, let's look ahead. Section 4, the road to 6G. Even as we're mastering 5G today, we have to keep our strategic planning guided toward the horizon. When you contrast the current limits of 5G against 6G's proposed performance thresholds, it becomes super clear that 6G is not just some incremental software upgrade. It is a fundamental, ground-up architectural redesign. Where 5G gives us enhanced mobile broadband, 6G is targeting terabits per second throughput. Where 5G uses intelligent management, 6G is aiming for true AI native and semantic intelligence. And where 5G provides decent standard spatial positioning, 6G is pushing for insane sub-10 centimeter localization. The emerging trends driving all of this are just fascinating. We're looking at AI native architectures where AI is baked into every single layer, turning the network into a system that proactively learns traffic patterns and optimizes itself. Then there's ISAC, Integrated Sensing and Communications. This basically transforms the radio access network into a giant radar-like sensing platform capable of tracking vehicles or even sensing human gestures in a room, all while simultaneously communicating data. Throw in the exploration of sub-terahertz bands above 100 gigahertz and the use of digital twins for predictive maintenance, and you're looking at a radically different technological landscape. The absolute core takeaway here is this. 6G represents a fundamental redesign of wireless communication, driven by intelligence, adaptability, and long-term energy efficiency to satisfy diverse use cases. The networks of tomorrow won't just blindly transmit data. They're going to learn, they're going to sense their environment, and they'll autonomously optimize themselves for maximum sustainability and peak performance. Which leaves us with one final, pretty provocative thought to wrap up today's explainer. How will you deploy these autonomous, sliced, and beam-centric technologies in your own enterprise environments? Whether you're mapping out a migration path from 4G to your very first private 5G proof of concept, or you're designing a fully scalable carrier-grade system, the tools to build the future are right here in front of you. Thank you so much for joining this module. I highly encourage you to get your hands dirty in the lab with these concepts. Maybe spin up an open source core and see it for yourself. See you next time.